Now that we understand the basics of what a thermostatic expansion valve is doing, let's think about how to charge it. It's important that we have the proper airflow first. And we're going to talk about airflow later in the course because there's a lot that goes into that alone. Right now we're going to talk about making sure we're feeding it enough subcooled liquid. So we're going to start with the outdoor unit. Now before we talked about target superheat and subcooling, we're still going to have to talk about subcooling, but we need a target subcooling. And that changes from manufacturer to manufacturer. But instead of having to find a formula or a chart or anything else, they actually simplify this for us. So this particular manufacturer has told us if we have an indoor TXV, our outdoor subcooling should be 12 degrees Fahrenheit. So that would be our target subcooling. Now, not every manufacturer gives this to us on the tag like this manufacturer. So not every manufacturer puts it on the outdoor unit. In this case, this manufacturer has told us, check subcooling and superheat. TXV application should have a subcooling of 8 degrees Fahrenheit plus or minus 1 degrees. So it's telling us exactly what they want for our subcooling. And that's going to be very, very important. So we're just going to pick one of these units. We're going to pick, say, a Goodman system. And our target subcooling is 8 degrees Fahrenheit. That's fantastic. Now we have a target, and the manufacturer told us what they want. Now, not every manufacturer has it easy to find, and if you can't find it, 10's a pretty common number to use, but I stress again, you want to go with what the manufacturer says. They vary quite a bit. On this paper, this manufacturer asked for 8 degrees target subcooling, what we're aiming for, what we want it to be. Next, we need to find out what our subcooling is. So we know the speed limit's 8. Let's find out how fast we're actually going. To find that, we're going to need to do a little formula. Liquid saturated temperature. That's going to be liquid PSIG converted to a saturated temperature. That's going to be on the liquid line of our condensing unit. The liquid line coming out. So let's do that number. Let's do the math. And let's say that number comes out to be 95 degrees Fahrenheit. That's our liquid saturated temperature. Now it says find the actual liquid line temperature. The actual liquid line temperature, we get our clamp thermometer, we clamp it on the line and get the true temperature. The liquid line coming out of the unit, we clamp it on that line to get the actual liquid line temperature. So let's say our actual liquid line temperature comes out to be, was 87 degrees Fahrenheit. Now our formula is the liquid saturated temperature of 95 minus our actual liquid line temperature of 87 equals a subcooled liquid of 8 degrees Fahrenheit. So 8 degrees Fahrenheit is what we're actually at. We have 8 degrees of subcooling, and our target is 8 degrees of subcooling. We're perfect. That's exactly where we want to be. We want to be at 8, we're at 8. Now that tells us that we're feeding enough subcooled liquid to our metering device. So if that number is correct, now I'm going to look at superheat to make sure that's correct. Remember, if we feed it enough subcooled liquid and have enough airflow, its job is to maintain superheat for us. We don't just want to assume, we want to also check it. We don't just look at one side of the system. But before we move on to that, let's look at some other scenarios. Let's say that our liquid saturated temperature was 95 degrees Fahrenheit. We get our clamp thermometer and we clamp it on the actual liquid line, and the actual liquid line temperature is, say, 80 degrees Fahrenheit. We take 95 saturated, PSIG converted temperature, minus our actual liquid line of 80, that gives us a subcooling of 15 degrees Fahrenheit. This would mean that we had an actual subcooling of 15. We want to be at 8, but we're at 15. The subcooling that we're at is too high. So we are significantly higher. So let's look at that again, what it would be if it was a tank. Let's say here was 8 degrees of subcooling. That's what we want. But if we look at how much liquid refrigerant, subcooled liquid refrigerant we have, we are much surpassed. We want this much subcooling, but we have too much subcooling. There's too much refrigerant in our condensing unit. Now the metering device isn't going to care. It says, hey, you can have all the extra you want. I'm just going to back you up in the condenser. The problem is it puts more pressure on the compressor and it restricts how much saturation we have. We're flooding the condenser and it's going to cause the system to use more electricity and wear out faster. So that's an issue we're going to have to take care of. So if our subcooling is higher than the target, we call this high subcooled liquid. We're going to convert that to words that's easy to remember, such as a flooded condenser. There's too much liquid in the condenser, so we use the word flooded. But not just flooded, specifically a flooded condenser, that component. Right, let's use the same exact number that we had. We have an 8-degree target where we want to be, and let's find out what our actual is. Let's give you some different numbers. Let's say our saturated temperature is still the same. PSIG converted to a saturated temperature. Let's say we're still at 95. Now our liquid line temperature, we put a thermometer on our actual liquid line temperature, and that temperature came out to say 94 degrees Fahrenheit. Well, we take 95 minus 94 and we end up with a subcooling of only 1 degree Fahrenheit. So our actual subcooling is 1 degree Fahrenheit. If we look at that differently, here's my 8 degrees of subcooling that I want, but I'm only have this much liquid in there. I have too little subcooled liquid. I don't have enough subcooled liquid in my condensing unit. So if we look at this differently, we can say a low subcooling equals a starved condenser. I do not have enough refrigerant in my condensing unit. If I do not have enough refrigerant feeding my metering device can't do its job for us. Now, just because we have a low subcooling doesn't mean we need to rush and charge the system. We still need to look on this side and see what is happening. It's very important. Now, subcooling is we focus more on with the thermostatic expansion valve, but we still need to look at superheat to see if he's doing his job. In other words, subcooling pays the metering device in subcooled liquid. If you're paying him enough subcooled liquid, giving him enough airflow, he should maintain superheat for you if he's working correctly. So make sure you make the notes. High subcooled liquid is a flooded condenser. Low subcooled liquid is a starved condenser. To find your target subcooling, you need to RTFM with the manufacturer's instructions or look on the tag, the data plate of the unit, and it somewhere will tell you. If you absolutely can't find it, you can go with 10, but I guarantee you every manufacturer has it somewhere. Some just make it easier to find than others. And just because it says indoor TXV subcooling doesn't mean there's actually one inside. This one says indoor TXV subcooling, but somebody could have installed it with a fixed orifice. So just because it says it wants 12 only applies if we have a thermostatic expansion valve located inside.